The research paper discusses novel error correction decoding algorithms for Reed-Solomon (RS) codes based on an earlier termination algorithm to find the error locator polynomial. The authors proposed two fast decoding algorithms, including the improved frequency domain modular approach (IFDMA) algorithm, which requires only 2 steps to solve the error locator polynomial, and the T0 shortened IFDMA T0s IFDMA algorithm for quick error number evaluation. These algorithms are designed to reduce decoding complexity compared to existing methods. The paper reviews the Welch-Berlekamp key equation problem and the modular approach (MA) algorithm, which is effective for solving the WB key equation problem. It also presents the MA algorithm and some related results, highlighting the key equations and the process of finding the error locator polynomial. The authors demonstrate the efficiency of their proposed algorithms through evaluations, showing significant reductions in multiplication complexity compared to existing methods. Here is a combined summary of the 2 pages. The paper discusses the termination mechanism of the MA algorithm for decoding LCHFFTBASEDRS codes. The MA algorithm is an iterative process that computes the error locator polynomial, and its termination mechanism is crucial for efficient decoding. The authors propose a new termination mechanism that allows the MA algorithm to terminate in 2 steps, where E is the error correction capability of the code. The authors first introduce 4 parameters, G, R, RANDD, R, which are related to the error correction procedure. They then present several lemmas that establish the relationships between these parameters and the iteration process of the MA algorithm. Specifically, lemma 1 shows that G, R, and RANDD, R, cannot be both 0, while lemmas 2 and 3 provide conditions for the termination of the MA algorithm. The authors then introduce a new termination mechanism, which is based on the concept of even R, I, 0, R, I, 1, the even element in R, I, 0, R, I, 1. They show that even R, I, 0, R, I, 1, is non-decreasing with respect to I, and that the condition R, I 0, 0 equals 2e and R, I 0, 1 is greater than or equal to 2e plus 1 is sufficient for the MA algorithm to terminate. They also prove that this condition holds when I 0 equals 2e. The authors then present a sufficient condition for finding the error locator polynomial, which is based on the value of d, I, j. They show that if d, I, j equals 0 for all 2t1 is greater than or equal to j is greater than or equal to I, then w, I, x, is the error locator polynomial. They also prove that this condition holds for I equals 2e. Finally, the authors outline their first decoding algorithm based on the IFDMA algorithm, which incorporates the new termination mechanism. The algorithm is designed for LCHFFTBASEDRS codes and is based on the LCHFFT-related algorithms. The authors claim that their algorithm is efficient and effective for decoding LCHFFTBASEDRS codes. The research paper discusses the encoding and decoding of LCHFFTBASEDRS codes. It begins by explaining the LCHFFT algorithm, which is used for encoding and decoding. The paper then presents the LCH extended IFT algorithm, which is used for the decoding process. The encoding process involves the use of the LCHFFT algorithm and one LCHIFFT algorithm, resulting in a complexity of O, NLG, n-k. The decoding process involves the use of the IFDMA algorithm, which has a complexity of O, TLG, T, for error locator polynomial calculation and O, NLG, n-k, for syndrome polynomial calculation. The paper also discusses the Qian search method and Forney's formula for error correction. Finally, it presents a first decoding algorithm and a second decoding algorithm, both of which have different complexities and are suitable for different scenarios. The first algorithm, our first decoding algorithm, is presented for decoding Reed-Solomon codes using the LCHFFTBASED approach. This algorithm employs the IFDMA algorithm to solve the error locator polynomial and has a lower multiplication complexity than the second decoding algorithm when the number of errors is relatively small. The second decoding algorithm is introduced, which uses the T0SIFDMA algorithm to determine the number of errors and the ESBM algorithm to solve the error locator polynomial. The T0SIFDMA algorithm is more suitable for cases where the number of errors is relatively small, and it can quickly determine the number of errors. If the T0SIFDMA algorithm does not return any value, it means that the number of errors is relatively large, and the first decoding algorithm can be employed. The parity check matrix and syndromes for LCHFFTBASEDRS codes are analyzed to show that the ESBM algorithm can be applied to find the error locator polynomial in the second decoding algorithm. The relationship between the syndromes and the coefficients of the error locator polynomial is obtained, and the matrix SE times E in the upper left corner of the Hankel matrix S is shown to be invertible. This allows for the calculation of the coefficients of the error locator polynomial using only two E syndromes. The SESBM algorithm is used to efficiently solve EQ 15 to get the error locator polynomial sigma x. It's summarized in Theorem 14, which states that given a positive integer t and an at times t plus 1 Hankel matrix S, if there exists a positive integer e and an unknown vector lambda e minus 1, lambda 1, t satisfying certain conditions, the ESBM algorithm can solve the error locator polynomial with two E iterations. The SESBM algorithm, presented in Algorithm 8, can solve the error locator polynomial with two E steps, where E is known. This algorithm reduces the multiplication complexity compared to the T0SIFDMA algorithm, especially when E much less than t. The coefficient vector of sigma x needs to be transformed into the LCH basis x for the LCHFFT algorithm in the second decoding algorithm. The decoding process involves calculating the syndrome polynomial, finding the number of errors, computing the coefficient vector, and then using the Qian search and FFT to find the roots of sigma x. The complexity of this process is O, NLG, R. The second decoding algorithm, summarized in Algorithm 9, further reduces the number of multiplications by using the Reed-Muller transform. This paper proposes an efficient termination mechanism for the MA method to find error locator polynomials by only two E steps in the error correction decoding process of RS codes, where E is the number of errors. Based on this new termination mechanism, two types of error correction decoding algorithms for LCHFFTBASEDRS codes are proposed, which have lower multiplication complexity than existing correlation decoding algorithms. The first decoding algorithm, based on IFDMA algorithm, reduces the number of multiplications by 41.79% to 5.64% for parameters n equals 256, k equals 224, and by 42.87% to 24.05% for parameters n equals 128, k equals 96, compared with the EFDMA algorithm. The second decoding algorithm, based on T0SIFDMA algorithm and SESBM algorithm, reduces the number of multiplications by 22.06% to 35.86% for parameters n equals 256, k equals 224, and by 24.05% to 42.87% for parameters n equals 128, k equals 96, compared with the first decoding algorithm. The paper also provides a comprehensive review of the literature on Reed-Solomon codes, error correction, and decoding algorithms, including the work of Berlekamp, Reed and Solomon, Dabiri and Blake, Chen, Trong et al., Liu and Liu, Wu, Lin et al., Tang and Lin, Fedorenko, Chen et al., Tang and Han, and Roth, Moon, Lin, Yu et al., and Hu et al. In conclusion, the proposed decoding algorithms are more suitable for the case of 2e less than t0 plus 1, and the essential reasons include the lower multiplication complexity of T0 SIFDMA algorithm and SESBM algorithm when e much less than t, and the effective reduction of multiplication complexity for syndrome calculation by the ERN transform.